There we have it. So big thanks to Seogi for being willing to jump in and give this seminar this month. As we've talked about, it'll be quite informal, so jump in, ask your questions, and we'll have this be quite conversational. So Seogi is a postdoc at Stanford. Many of you know him. He's a very active contributor and one of the founders of the SimPEG project. And the title of his talk today is How Do We Plot a Resistivity Model from Airborne EM Data? So go ahead, Seogi.
Thanks, Lindsay. I'll just share my screen. Is the presentation showing up?
Yes, we see your slides. It's not like in present mode, but we can see your slides. Now it's in present mode. Excellent.
Yeah, so as I kind of briefly said before, the title is How Do You Plot a Resistivity Model from Airborne Electromagnetic Data? So it's much low-key kind of talk. So it's not going to be very technical, but as I said, I kind of want to share just the bits and pieces of tools that I use when I am visualizing and analyzing sort of the result of the inversion, which is the resistivity model. So Airborne electromagnetic method, just in case there are probably some people who haven't heard of the Airborne. So this is like a typical Airborne electromagnetic experiment. We've got a helicopter here, and then we have a loop. So the typical loop of Airborne system, it's about 11 to 12 meter or 10 to 12 meter. So it's a big loop if you think about it. It's probably bigger, much bigger than your room. And then what we do, we inject the current. Then the current will generate the magnetic field. And then the current is time varying. It'll generate time varying magnetic field. And this time varying magnetic field will interact with the subsurface material, which is a conductor. So if you think about the air, it's an infinite resistor. So there will be lots of currents flowing within the ground. And then sometimes we call that as an induced currents in the subsurface. That induced currents will generate the magnetic field that we can measure at this receiver loop. And then that data is often in the form of the induced voltage. Okay. So that's the typical AEM experiment and the induced voltage that we measure, depending upon the type of the survey. So sometimes you could use the frequency domain system or time domain system. The one that I explained was a time domain system, and that's we have the multiple time channels of the data that we can obtain information about the subsurface resistivity. And the early time usually includes information about the near surface, and the later time includes information about the deeper part. So to sort of the analogy in frequency domain, if you have a high frequency data that kind of contains information about the near surface, and if you have a low frequency data, it contains information about that deeper part of the surface. And once you obtain the data, this is a sort of the model that you can obtain. So this was sort of one of my latest paper, and this is somewhere in Northern California. And the scale is about 50 kilometer in the length scale. And the depth, what we're seeing is about 300 to 400 meter. And the blue color is a low resistivity, and red color means the high resistivity. So blue color, this was the purpose of this survey was in the context of mapping hydrogeology of the subsurface. So people were interested in what is the sediment type of the subsurface. So blue, which is a low resistivity, corresponds to fine-grained materials like clay and silt. Red means coarse-grained material like sand and gravel. So coarse-grained material can be sort of the pathway of the water. Fine-grained could be a barriers of the water flow, which is an important information to understand the hydrologic system. Okay, so that's kind of what airborne electromagnetic method is. And what's exciting as an electromagnetic geophysicist, the use of AM method is rapidly increasing. So this is an example of AusEM project in Australia. I don't exactly know what is the length scale here. It'll be much bigger than 100 kilometers, like I don't know, thousands of kilometer length scale, which is huge. And this is the amount of data that they covered with the airborne EM. And you can already see some sort of spatial patterns of the resistivity, which is pretty cool. So this is a nationwide survey and the typical line spacing of the AM data. So when we're talking about airborne data, we usually talk about what is the line spacing, because you fly over a large area, but depending upon the line spacing, the amount of data that you acquire might be quite different. And then I think the typical line spacing used for this nationwide survey is 5 to 20 kilometer line spacing, which is pretty large. Okay, and it was for various purposes. I think the major purpose was minerals, but I think there are some purposes for waters and other stuff as well. And what's really exciting is all of this data, so the measured airborne data in the form of voltages, as well as the resulting resistivity model by interpreting the airborne EM data, is available through this website. That means we have lots of resistivity model that you can potentially use almost for free. Okay. And this is another example, a little bit smaller scale. This is led by USGS and Bert Minsley's group. So this is an airborne EM project in the Mississippi alluvial plain. This was very specific for hydrogeologic mapping. And this is more like a statewide survey. Here's this boundary shows the states in US. And this is, I think this is the Mississippi River. And then if you look at the scale, it's about a couple hundred kilometer by a couple hundred kilometer scale. Again, really, really large. And then the typical line spacing here was about 3 to 6 kilometer. And the total line kilometer. So when we're talking about the amount of data that we acquire, usually people use like a line kilometer. So that's the actual amount of AM data. And then you can look back, okay, in 1 line kilometer, how many soundings you have, then you can sort of calculate how many data points you have. Anyway, so it's about 43,000 line kilometer, which is a lot. And that sort of the typical size that we do, it's about like 800 line kilometer or 1,000 line kilometer. So it's about 43 times of those surveys, which is a huge survey. Okay. And the other example is CDWR. It means the California Department of Water Resources. So this is the governmental sector basically kind of managing the water, groundwater, as well as surface water in California. And they are running a relatively large scale airborne EM project, basically covering the entire Central Valley of California and some of the water basins in California. So this like a red color is the scheduled AM survey for the next 3 years. And this green color means it's already acquired data. And I think the black line shows the flight line. So this is where the Salinas Valley, you can see this is the Monterey. Not sure if you haven't been there, it's a beautiful place to go. But they have quite a bit of groundwater issues because we need the seawater intrusion. Anyway, so there are lots of airborne EM data coming as well. There are already lots of airborne EM data available, but there are much more airborne EM data coming and emerging, and that will be available to the public. And that's sort of the bottom. That's sort of my pitch. Okay, why it is important? So we have lots of airborne EM data as well as the resulting resistivity model from the airborne EM data, and they are freely available. So it is important to understand what is that then resistivity model from AM data means, and how to really even plot it up. How do we load it up and plot it up, and then kind of explore those sort of data or resistivity as a data to understand the subsurface. And depending upon the problems you have, you may want to use different sets of tools and ideas. So that's sort of the kind of like my motivation of today. And I kind of want to start with the first question is how do we obtain a resistivity model from airborne EM data? And we're using what we call inversion technique. And there can be many different types of inversion. And I'm going to introduce a specific technique, which basically use a one-dimensional assumption, layered assumption. And suppose so here's a simple example. Suppose we got the true resistivity model. Red, again, high resistivity. Blue means the low resistivity. So red, you can think as a coarse grained material. Blue is a fine grained materials. There's some sort of layered structure. And then if you have a helicopter here, do an AM experiment, that's sort of the data, form of the data that you can obtain. So this is in voltage at multiple time channels. And typically you got maybe 20 to 30 time channels. And this data, by looking at the data, you may not have much idea. So what we want to do from this data, we want to find a resistivity model of the subsurface in one dimension that can explain this data. And that's what we call inversion process. And for a single sounding point, you can have 1D resistivity model like this. And if you move to another place, then you can have another 1D resistivity model. And you have many sounding location. And by doing so, by repeating the 1D inversion, you can have a stitched 1D resistivity model like this. But doing this inversion separately, it's somewhat cumbersome. And then sort of you're ignoring the possibility to sort of like regularize this resistivity value in space. Suppose like if you're interested in hydrogeology application, and if you think about the general like a structure of hydrogeology is layered. So you would prefer sort of the smooth variation of resistivity in lateral dimension. And that's sort of the major idea of what's called spatially constrained inversion developed by Visali et al. 2008. And the idea is simple. Rather than doing a separate 1D inversion, we're going to invert all of them together, but the regularize, like put a sort of prior information that the resistivity value between the sounding are smoothly changing. Okay, so that's what's called spatially constrained inversion, and that's sort of the kind of typical tool used when interpreting airborne electromagnetic data as a first path. So that's the tool. And if you apply the data, airborne data, and then apply the inversion, now you can actually obtain a resistivity model. And potentially that would be sort of the first point that you can be exposed to use this airborne electromagnetic data. And the question is, like, how do you plot a resistivity model? And that was sort of like kind of intro of this talk. And now I'm going to do a demo. See, I want to show my calendar. You guys all know my calendar schedule, so it's fine. Yeah, so this is a notebook that I put together, and I think it's actually available through this GitHub repository that I will post in Slack channel later. And I think this video is available later, so you can actually use it as well. Is Jupyter Notebook kind of readable?
Yeah, I can see it.
Okay. So yeah. So what I'm going to do within this notebook, I'm going to kind of show various different ways how to plot it up, the resistivity model. And then I'm very focusing on the specific form of the inversion, because as I said, like we are inverting for basically 1D for each sounding. And then so each sounding location have X number of layers and then like X number of resistivity value for each layer. Okay, so that's sort of the data. And I'm loading up a couple of packages. And for SimPEG users, currently it only works for EM1D branch, specific branch, but we'll soon merge those into main SimPEG branch. So you probably don't need to use a specific branch. And this is a simple, like a function that I wrote to read what is the data. And so some like again, there's no universal form people are exporting their data set. So this is also a very specific, but what's the typical tool used in California is what's called Arhu's workbench. And that's this is the function that can read the exported form of their resistivity model. So this resistivity model called like blah, 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 .xyz. This actually model is in the GitHub repository, so you can use it. If I run it, and without too much explanation, it could run and then obtain the pandas data frame. So if you look, this is actually the table that you can obtain, and then that is basically the resulting resistivity model. So there are many different columns. So for instance, there's a line number, which is important. And and UTMX, XY coordinate. And timestamp is actually, they record the time, then they convert it into like some floating number, but basically it you can actually backtrack what is the ordering of the sounding. Or you can use what's called FID. It's a fiducial. It's an ordering of, you can actually think that as a sounding number, but the sounding number includes the sort of order of the operation, order of the survey. So this is actually important sometimes, because if you want to plot a resistivity model, let's say in the direction of a survey, and then actually you need to know which one was the first. Let's say you have a line, and then you want to know, which one was the starting point. And that's actually important information to know, okay, the direction of time was like that. So that kind of gives you an idea. Yeah, there are quite a few other things which I wouldn't explain. And the other thing was topography is based on XYZ value at each location. So this was the location of each sounding and the elevation of the surface elevation. And resistivity is the recovered resistivity model as a matrix, and then the shape. So that means that there was 18,000 about soundings, and the number of layer was 40. Okay, so that's what it includes. And the line was basically the line number. The line number, the shape of the line number is the size, number of sounding. Okay. And you can calculate the unique line. Then there are lines. So there was the 43 unique lines. Okay. And as a Simpac kind of style, we vectorize a model. So what I do, resistivity was a matrix. And the shape was like that. And I flatten and then vectorize. So this is where there's a bit of inconsistency in the 1D code, because the typical ordering of Simpac is X, Y, then Z. But here I first use the Z, then radial, a radial direction or sounding number. Okay. But later we can change this, but this is sort of the current structure. Okay. And then I also put the timestamp. And now you can actually plot it up. So this is just a scatter plot at X and Y. And I'm plotting up the topography. So the blue color means the low and yellow color means high. So as you go to the east, you can see the topography is going up. This is where actually the Sierra Mountain was located. This data is from somewhere in California, close to the mountain. Okay. And there are a whole bunch of other things that you can plot it up, but I wouldn't. Let's say, maybe I could actually plot it up. Let's say the timestamp. Oops. So you can see the time as well, which one was the first. I think they probably started somewhere in the blue color and then slowly moving to the west. And then I think this tie line, or this sort of horizontal line, was acquired at the last. Okay, so you can take a look at that. Now, I'm going to use what's called stitched 1D model. And this is the function, that you can import from here. And I'm not still debating what's the name of this sort of class. Currently I named it as a stitched 1D model. And then it's a function that kind of allows you to just explore this resistivity model and then plot it up. And I'm importing two functions, stitched 1D model and the plot layer. And then stitched 1D model input of this object is topography, line, and H was the vertical discretization. So start with 3 meters and then slowly increasing with some sort of geometric factor. And then I also need to input the timestamp. As I said, we need to know the ordering of the survey to plot up a line. And the physical property is the resistivity value as a vector. Okay, so if you instantiate it, like we have now a model. And so as I said, for each sounding point, we have a resistivity model. So sort of natural pathway. Okay, let's look at a sounding location and plot it up as a function of vertical profile. Okay, so let's start with sounding number 0, and then resistivity was ordered as like a number of sounding by number of layers. So you can just put the I sounding and you can plot it up. You can use this plot layer function to plot it up a resistivity, vertical profile of the resistivity. You can change the sounding number, and you can see different resistivity values. And well, if you want to look at kind of many resistivity model together, then you could, not together, but as an interactively, so you can actually just generate that little app, and you can see different resistivity. It is changing, so it means the Earth is not uniform, and it looks smooth. Yeah, so you can probably spend hours to look at this, but let me just move on. Okay, so that was sort of the plotting in a one-dimensional, like a vertical direction, and that's fine. And but the typical way to plot the resistivity model is the 2D section plot, or so that's what I am going to do. Then, like, you need to know where is the line, like which line is where. Okay, so that's this kind of the plot shows how to do that. Like, so we have a unique line. I think we got 43 lines, and then line was including it. Line has the number of sounding location, so it's same as the number of location we have. So we're finding an indices for each line. So if I put line 0, it's here. The line number was 1 blah blah 1 is 2. If you change that, you can look at this. So you can see where is the line, each line is located. And again, you can write a simple function and make it interactive. So you can look through which line is where. Okay. So once you recognize the line that you wanted to see, oops, it's too big. It was 43. So that's fine. Then now you can actually use that model object that we generated, that we initiated in here. Okay, so I'm using this object to plot it up, a vertical section. And let's say we plot so that looks like that. And I think the line number for this line was 23. So let's look at this. And so this is the distance, okay? And but you can plot it up an easting direction. So now it's an easting direction, or like it's an option. You can plot it in the northern direction, which doesn't really make sense. It will look ugly, but you can do it.
Sonia, one quick, maybe simple question for you. How did you choose the width of how wide you're going to plot each of the strips?
That's a great question. I think that's the next step that I was going to introduce. And oh, shoot, I need to let me go back. I'm going to change that to a distance. So, so one point before I go there, it's like if I need to choose the distance, so it's a relative matrix. So I'm counting the starting point of that line and then calculating sort of the effective distance, and then in the direction of the flight. So that was the reason why I needed to have the timestamp when we're when they're initiating the model object. Anyway, so Lindsay's question was, okay, how do we decide the it's actually too big, so let's do that. Huh. Ah. So this is actually what I'm doing. I'm not. It took a while to figure it out. Maybe actually I could actually change it. Yeah, that's probably a little bit better. So Lindsay, what I'm actually doing under the hood, so I'm basically using the p-color mesh for each of the sounding location, and then setting the DX. So this is the DX that you need to set it up. There's a default value. And currently, I think it's probably like a 50 or something like that. And that's a relevant number for AEM to fill in. So like if you don't like kind of having this space, then you can basically fill in by increasing this number, right? So let's say 15. And then now you can actually like plot like a 2D model. So this is kind of sort of trick that I was using, but if you look back, it was, whoops. See, now you can see the scale of the problem that we're working, and the aspect ratio is important to set it up. So if you look at that, it's almost like a 2D plot. But what I was doing was basically a whole bunch of like a 1D plot, and then stitching together. Okay. So this is kind of, and I think as the data gets bigger, you may not want to do every sounding. So I probably need to change the code a little bit to do a little bit smart. If that's greater than X number, then we just downsample, but I don't really do it at this point. So sometimes if you're just dumping in million points and trying to plot up a line, it'll take a while. Anyway, so that's the 2D code. That's the 2D section. And actually, basically, I sort of treated most of things. And then if you don't like the turbo, you can go back to jet or there it is, whatever color map that you like. And you can change the color scale. Like if you don't like 100, then you can change 2000. Okay, so that's sort of the section view. So now that was a sort of 2D section view, but how about the plan view map? So what we did, we just look at the single sounding location, look at the vertical profile, and then we look at a line, and then we can plot it up as a section of the resistivity. And what you can think about, so for each layer, we can plot up the resistivity values. So here I'm starting with I'm using the scatter plot. This is the first layer. So you can see some resistors here and some conductors. And this is actually where the river flows. So along the river, you got lots of coarse-grained materials. It is kind of makes sense. Okay, if you have a river, we're expecting to have a bit of like lots of coarse-grained resistive sediments. So it was kind of reasonable. And if you want to see the layer 1, doesn't really change, layer 2, layer 3, layer 4. Again, you can actually put together as a little app. So you can 2, 3, 4, 5, 6, 7, 8.
Seogi?
Yep.
When you say the layers, is that because you use the same 1D mesh for all the sounding?
Correct.
Okay.
Correct. That's the underlying assumption. So yeah, so that's spatially constrained inversion. Each sounding assumption under the hood is each sounding has the same number of layers.
Yeah. Can you remind me again how you handle topography when because the sounding might not be like
I don't handle the topography. So okay. So there's no although the code actually takes the topography, but when you're regularizing, we just that lateral constraint, it threw the layers.
Okay.
So which I think still okay, but you're right. But if there's a structure that are not aligned with the topography, then I think we're putting a wrong prior information.
Okay. Yeah. Thanks.
So now,
just as a note, it might be helpful to include not just the layer number, but also the depth interval that you're looking at.
Absolutely.
Because 15th layer doesn't mean too much to me.
Absolutely, absolutely. This is just a mock-up that I generated for this presentation, but absolutely we can
And
put
it is really cool.
right. Yeah, so here what you're seeing as a resistor is actually the bedrock comes in at the Sierra Foothills. So you can see kind of interesting variation of the resistivity in a two-dimensional space. Okay. So that was the 2D, but as a point. So we just plotted up each sounding location as a point. But some people doesn't like it, and then some people want to see that as a surface. So how do we like interpolate these points into a 2D surface? And again, I'm using a very simple form, which is inverse distance interpolation. So there could be a whole bunch of different interpolation that you could potentially use it. I personally like it because it's simple, but kind of aligned with what we're doing, because what the geophysics does is an average of resistivity value in the subsurface. So inverse distance weighting is based on an average of a whole bunch of resistivity value close to a whole bunch of sounding close to that location. I kind of like that. And again, there could be many different tools that you could use. What the inverse distance interpolation takes is the XY location of the sounding. So topography was basically the XY location of each sounding and the elevation. So I'm not using the elevation. Elevation was the third column. And so you can actually input the resistivity value for each layer. And the dx and dy is the discretization in space. So the output of this interpolation is a two-dimensional grid. Okay. And we're using sort of the uniform mesh. So you can change if you like, if you don't like the 200, you can change. So I could start with even bigger. So if you decrease the dx and dy, there will be many more cells. So it'll take a bit of time. But if you coarsening the cell size, then it'll take much quicker. Okay, so I'm just gonna do 10,000 and then start with 1. Yeah, so what the k nearest points, it means how many points that I'm going to use for this interpolation. So if you actually only use 2, then this is the 2D map that you would get, which is not very satisfying, I guess. So you can play with it, how about 10? Yeah, it doesn't look good. 20. Still, 30. Gets a little bit better. Okay. I think it was actually 100 that I used. It looks not bad. And they're probably it covers much bigger region than that we have the data. So this max distance is handling that. So rather than using 10 kilometer, so what it does, it calculates for each of the points, 10,000 is the distance that we're interested in. That's what we're seeing. So here, let's say if you use 1,000, then that'll look like that. So now it looks much more reasonable. You can increase a little bit, let's say 2,000. And that looks like that. So compared to 1,000, it looks much more pleasing. So it's just a matter of how you set the parameters and make it kind of a reasonable plot. So let's go back to 2,000. And now you can play with the k nearest point. So 2 looks quite choppy, but then if you increase that to 100, that looks a little bit more pleasant. Okay, so that's the way that you can generate the 2D surface using this inverse distance weighting function. And so now actually we dealt with 1D and 2D, but the actual model is in 3D. So how do we plot up the 3D model? And I'm not sure how many of you have, go ahead.
So yeah, sorry, maybe a side question, and sorry if I missed it if you said it earlier, but so for this inversion result, you did use a laterally constrained strategy is to invert the sounding, correct?
Correct.
But so my question is, like, some of your sounding are very far apart. So did you, when you stitch things together, was there also like a maximum distance on how to like regularize only between two sounding if there is like a distance less than that, like, I don't know, like 100 meters between each sounding or something? Because I can imagine, like, here at the centers, for example, if you try to regularize on the side, it's going to be a fairly big jump. So the lateral constraint assumptions might not be, like, the lateral continuity assumptions might not be true at that scale.
Yes, I did have that constraint. So you can set the maximum distance that you want to regularize. So that was an input. So actually, that did cause a bit of problem sometimes, because you're not like if that's really far away, if you're still trying to regularize, and if the 2 points have a different structure, that's not anyway.
Awesome.
So the third part, like where actually you want to plot the model in 3D. This one was very specific for the tool called Leapfrog. It's a commercial tool, which is not open source, but it seems like a well-used tools. And then I'm not sure you guys are using. I am using it sometimes, mostly for visualization. So like this is a tool, a function that you can basically output that resistivity model into a format of the Leapfrog, and then I just gonna show you a quick example. And the model that we plotted looks like this. So this is the type of resistivity model, like a 3D view of the resistivity that you can generate with the Leapfrog. I'm pretty sure we can do this like using the PyVista, like an open source tool, but I haven't tried yet. Anyway, sometimes like commercial tools has pretty visualization, so I use it. Not always. And but the more, so that was like basically just plotting the resistivity model in the 3D space. But the typical way that we used to plot in Simpac or in UBC was using a 3D grid. So you can actually, rather than like plotting a resistivity value at each sounding location, you can interpolate and plot it up as a 3D grid. So that model object has an internal function that you can generate the 3D mesh. So if you do run the get 3D mesh, it runs. I think the default number of X and Y is 100. And so this actually is fixed, but you can actually change if you like. So let's say if you set the X is 400 and the Y is 400, and it'll, not 40, it will change. So number of X and Y. So you can kind of change the dimension or size of the mesh. So I'm just going to use the 400. And here it has the function that you can actually generate an interpolation matrix. So what I'm doing, I generate an interpolation matrix, then you can actually reuse it for many resistivity models. So again, I think it uses the inverse distance weighting. If you're curious, I can talk about that, but at this point I wouldn't do it. I'm just going to run it.
One quick question for you. How are you handling Z in that example? Because now we have topography. So are you just assuming basically there's no topography, or is there something else going on?
In this example, there is topography, but when I am interpolating, I still, so, okay, so I'll explain it. So what I did, I'm not sure that's actually making sense, but I think in terms of a good image, good looking image, it was much better just doing a 2D interpolation first. So if you got each layer, so you do a 2D interpolation using the same function that I have shown. So that's the reason why it asks number of points. So it calculates like an inverse distance weight and then average over to that 2D surface. And then you do that for each layer. Then I do a 1D interpolation for vertical direction. So that's how it's set up. And then you can actually generate some sort of sparse matrix that you could do that process. So that's how I do it. And then
the cell, like the thickness in the Z direction that you pick, is that like automatically picked based on the your layer thicknesses?
I think that currently, I think it's, not sure what is the default. It's probably 5. Again, this was very specific for the Airborne case. Oh, actually, yeah, I think I do. Yeah, I do. I do an okay job, I guess, for picking up. I forgot about that. But you can actually set if you like. So you can set 5 or something like that.
Okay, cool.
And I think it'll take a little bit of time. And once that interpolation matrix is generated, then you just need to pass this resistivity vector to this function. And then it'll just operate that matrix vector multiplication. Then you got the resistivity 3D model. Okay. And this function is the same purpose of masking the cells that are far away from the sounding location. So if you put the maximum distance to 3000, it'll only plot like a resistivity, the voxels within the 3000 meter distance from the sounding location. So once that's done, you could output it in the UBC format. Actually, the LibFrog supports the UBC format. You can plot it up, or you could use the ParaView or PyVista to plot it up. And if you plot that up, that looks like this. And I think, let's say, we could change this to 5,000. And I think, yeah, so that looks like this. So you can fine tune things like this, like let's say, go back to 2000. So really depends upon what you prefer and then what you want to show to sort of the consumer of whatever model that you provide. So it was kind of like it for the plotting. So I started from the 1 dimension in the vertical direction and expanded that to the 2 dimension, which was the vertical section. And then we plotted up as a plan view map. And then finally plotted up a 3D model, just the actual resistivity value that we recover from the inversion, and then interpolated that onto a 3-dimensional grid. So there are various forms of kind of various different ways that you can plot this up. And what kind of, it's a little bit scattered at this point, but I think I kind of put together as a Jupyter notebook that potentially could be useful for all of you. I think I have 10 minutes. So I'm actually going to, any question? By the way?
Yes, if I may.
Yeah, absolutely.
Yeah, my name is Jaap Mond. I'm wondering, your Jupyter notebook, is that running in a particular environment so that anything you like to use is available, or do you run it and then it will retrieve what you need to run the Jupyter notebook?
Can you repeat your question? Sorry.
Yeah, so the question I have, do you run the Jupyter notebook? Do you run it in a particular environment so that everything you need is available in that environment?
Yes. So so here's the kind of the GitHub repository that I put together. And I think it's slightly different, but I think because I gave a talk to our group, but basically it kind of answers your question, like how to put together an environment that could replicate sort of the Jupyter notebook that I have shown today. So yeah, all you need to do is go into this GitHub repository and look at the environmental file. And then you can actually use the conda to replicate the version, all of the version of the package that I have used.
Okay, thank you.
Any other questions? If not, so yeah, so that was cool to, well, I'm not sure that was cool, but it was okay to see how we can visualize the resistivity model. But then, okay, that's available, so I can plot it up, but actual data is available. So but what's provided from this, whatever the past project, is a single resistivity model. That's often the case. But the fact that inversion process is non-unique means there are many, many different resistivity models that can fit the data. But what we have seen is a single resistivity model. So there is always chance you can actually go back to the raw data or process data and reinvert with the different sets of prior information and or different types of code and regenerate the resistivity model for the purpose of your project. So that's where you need to actually use some of the numerical code that can invert the data, and that's what SimPEG EM1D code serves for it. So here's our AM data, and then when it supports, it can actually invert them and obtain a resistivity model. And again, what it provides is what's called spatially constrained inversion, which basically uses a 1D simulation, but stitch them together, but regularize in the direction, like in radial direction of each sounding. Okay. So I'm going to show, so that's like, okay, then there are a lot of open AM data. How do we invert that to obtain a resistivity model? And that's the next, whoa, it's very hard to see my banner. I'm just going to make it small. Version. So here I am using the frequency domain as an example because it's much quicker. Time domain is a little bit slower than frequency domain EM, but you can actually use the same structure and without too much. So here, what we're doing, we're generating the synthetic data. And this is the sounding location. And that is the true resistivity model. And let's see. So here I'm running the simulation to generate the predicted data. So we got 132 datum. And so we only got single line, but we still do this triangulation. So Thibault, this is where kind of what you kind of asked, like, okay, so we got many simplexes or vertices or edges that were kind of connecting to each point. And if you don't put anything, that is sort of, we're regularizing through each of these edges. We're minimizing the difference between these points. Okay, that's the regularization that we're putting in. But if you don't, let me return this point again later, but I'm just going to run it. So here we set the error, relative error, to 3%, but I actually didn't add the noise. So let's actually add the noise. So it runs the inversion, and then it kind of ran 3 iterations and reached to the target misfit. So this was the true resistivity model. That is the 1D resistivity model that we generated. Okay, so that's fine. So rather than, so we just set a single line. So let's increase the line to 5. So NY was the number of lines in Y direction. So now we got actually sort of the 3-dimensional survey. And I'm plotting up a single line here. And let's rerun it. And now we have a little bit better. Just gonna, like a kind of the linear triangulation looks a little bit more reasonable. And Thibault's point was, okay, sometimes you may not want to kind of like connect these lines, okay? Because depending upon the scale, like 100 meters is way too far. So you don't want to regularize it. So let's say the structure, the correlation length of the structure is less than 100 meters. You may not want to put the regularization in between. So this is the function that you can use. Let's say if you set the maximum distance to 100. And that black lines, it's kind of, let's make it a little bit better. So that's a little bit better. So this is the connecting points. So by increasing a little bit to 150, let's say, Actually, I should have decreased. Yeah, so then I think it's more like you're just regularizing within the line. And
But Sag, the regularizer is 1/dl, so it shouldn't matter, right? Like the smoothing term is going to go to 0 if the distance is large.
True. So you can actually still put it in, but so that's a good point. But something that I think it's hard to tell like whether that actually kind of still like there's a potential that could actually still make an impact because like you're still regularizing it, although you're rating. And actually, yeah, the reason why I kind of did it because I didn't take it. They didn't take account the length scale at that point. So yeah, I think if you actually take account the length scale, you may not need to do it. But this is anyway a function that you could use it.
Does help you speed up your inversion by reducing the number of nodes that are connected?
No, I think it doesn't really matter. In terms of speed, like it's probably equal. The regularization function, like it's pretty cheap. So it ran it, and you can actually get the model like this. If you like, you can actually generate that. So you could do the same exercise, like just generate the. Oops. And yeah, we can also generate this three-dimensional resistivity model that I wouldn't plot today, but that's how it is. And final thing that I want to comment. So the SimPEG EM1D code is actually now, it looks like almost like a 3D code. So you can actually use the same survey structure that you used for 3D simulation or inversion code in 1D, which was sort of the major kind of improvement that we made. Anyway, that was it for the inversion. And yeah, so that was it. And I'm kind of, for the context of developing that EM1D code, yeah, I'm planning to develop kind of a functionality to address the arbitrary shape of the loop source. Like, so currently it can handle the circular loop and the vertical magnetic dipole. So I'm going to expand that to, that can handle the arbitrary shape for majorly kind of for ground loop EM survey. And another thing that I want to do is inverting for the layer thickness as well as the resistivity value. And the third one, I'm not sure that I have time this year, but hopefully we could revisit the airborne induced polarization. So currently 1D code can handle the simulation of airborne induced polarization, but inversion has not been implemented yet. So it's sort of on my radar. Yeah, so that was it. Thank you.
Thanks, Zach.
Nice, thanks, Seogi.
Seogi, do folks have questions? And we're on the hour, but if people want to stick around and chat, you're more than welcome to. Fair enough. Well, I'll stop the recording, but if people do want to stick around and chat, you're welcome to. Thanks everyone for coming, and big thank you, Seogi. That was a really nice walkthrough and really practical. I really enjoyed this style of seminars, so I hope that inspires others to maybe show some work, pull up some notebooks and code at one of the upcoming seminars. Thanks, Seogi.
Thanks, Lindsay. Thanks all.
Thanks,
Bye, everyone.
Seogi. Need to jump.
Here's Zach.